Hey everyone, and welcome. You ever look at a flock of birds turning in the sky and wonder, how on earth do they do that? Or think about how simple cells in your body form incredibly complex tissues? It really does look like magic. But so often, it's all powered by these simple, kind of hidden rules. And today, we're going to pull back the curtain on one of the most powerful ones you've probably never heard of. So let's just jump right in with a couple of head-scratchers. First, how can a solid, a crystal, suddenly start to flow like a liquid without actually melting? And second, how can a bunch of individual cells with no boss and no instructions spontaneously start pulsing together like a perfectly tuned machine? It sounds impossible, but the answer to both is actually the same elegant idea. To figure this out, we first have to kind of reboot our whole idea of what a swarm is. Let's start with the picture most of us have in our heads. Yeah, when we see that flock of birds, we think they're all playing a giant game of follow your neighbor, right? Everyone is just trying to match the speed and direction of the guys next to them. That's called mutual alignment. It makes sense. It's a social thing. But what if the real secret to all that beautiful coordination wasn't social at all? What if it was just physics?
And this right here is the key difference. On the left, you have mutual alignment. That's watching your neighbors. It's an outward-looking social rule. But on the right, that's where things get interesting. Self-alignment. This isn't about looking at anyone else. It's an individual physical rule. It just says that you tend to line up with the direction you yourself are already moving. That tiny little change in perspective, well, it changes absolutely everything.
So let's really dig into this one ingredient, this idea of self-alignment, and see how it builds up into something truly spectacular. Okay, so the official definition sounds a little dense, but what it's really saying is there's this physical connection between an object's orientation, which way its nose is pointing, and its velocity, which is the direction it's actually moving. It's not a choice. It's a physical tendency, just a consequence of its shape and how it moves through its environment.
So where does this tendency even come from? Well, it's surprisingly simple physics. Think about it like this. Imagine a toy boat that's a little bit lopsided. If it starts moving, the drag isn't even. It creates this little twist, a torque, that automatically pushes the boat to straighten out and face the direction it's moving. That's it. That's self-alignment. There's no brain, no decision, just physics doing its thing.
Now this is where it gets really cool. Let's see what happens when we just let this one simple rule play out. We're going to start with just one single particle and watch what happens. Everything that's about to happen comes down to this one little ratio, called tau zero. You can think of it like a cosmic tug-of-war. On one side, you have the particle's internal drive to move and self-align. On the other, you have the forces from its environment trying to hold it in place. And when that drive to move finally wins, when this number drops below 1, the system hits a tipping point, and the real show begins. So, when that ratio is high, when the container's forces are winning, things are pretty predictable. You put one of these self-aligning particles in a little trap, like a bowl, and it just works its way to the edge, points out, and stops. It just sits there. We call this the climbing state. Stable, sure, but also kind of boring. But the moment that ratio dips below 1, something amazing happens. With no push, no new instructions, the particle just breaks free. All on its own, it spontaneously starts moving in a perfect stable circle. It just picks a direction, clockwise or counterclockwise, and goes. This is a dynamic, stable state that just emerges from that one simple rule.
Now, drift pitchfork bifurcation sounds incredibly complicated. But all it really means is that this sudden jump into motion is a totally predictable event. Here's an easy way to think about it. Balance a pencil perfectly on its tip. For a second, it's in a stable state, not moving. But you know it has to fall, right? It will inevitably fall into one of two new stable states, left or right. That's exactly what our particle does. It goes from the stable state of still to the new stable states of orbiting left or orbiting right.
Okay. So one particle orbiting is pretty neat. But what happens when we pack a whole space full of them? This is where we answer that first puzzle from the beginning. At first, if you jam a bunch of these particles together, you get, well, exactly what you'd expect to get. A solid. A perfectly ordered, motionless grid of particles. A crystal.
Everybody's locked in place by their neighbors. But then you flip the switch, you activate self-alignment, and the entire solid structure begins to move. It flows. It's not melting. It's actually sliding along these internal lines, but it keeps its solid crystal structure the whole time. It's called a Rio crystal, a truly weird state of matter that's somehow both a solid and a liquid at the exact same time. So we went from a single orbit to a flowing solid. Now for the final leap. What if these particles are actually connected to each other? Like with little springs. You know, the way cells are connected in the tissue.
The result is something scientists call collective actuation. Basically, that little orbiting tendency of each individual particle gets shared and synchronized across the entire system. And the whole thing just comes alive. It starts to pulse and oscillate perfectly in sync, like a single massive engine that powers itself. It becomes that ticking clock we talked about, built from nothing but simple parts and one simple rule.
And what's really wild is that we can actually direct this machine. Check this out. If you pin the whole material down at its edges, you get these beautiful, synchronized, swirling motions. But if you just pin it in the very center and let the rest be free, it starts twisting back and forth like a metronome. We can completely change the collective behavior just by changing how we hold it.
And this is not just some cool computer model. I mean, this is real. Scientists have seen these exact same dynamics, the swirling, the twisting, in real-life biofilms of bacteria. It's proof that self-alignment isn't just a clever idea for a simulation, it's a fundamental principle that's actually at work out there in the biological world.
So, we've got orbiting particles, flowing crystals, and living machines. It's all fascinating stuff, but what's the big picture? What are the real-world takeaways from this little hidden rule?
Well, the applications are enormous. For swarm robotics, it means we can build swarms that coordinate using way simpler physics-based rules instead of complex code. We could create incredible new metamaterials that can literally move on their own, or change shape, or even heal themselves. And maybe, most importantly, it gives us a brand new window into understanding how life itself gets built, from how our tissues form to how bacteria build their colonies.
For anyone trying to build things, this is the real game changer. This quote nails it. A robot built with self-alignment doesn't need fancy sensors to see how fast its neighbors are going. The smarts are literally built into its body. All the computation is done by physics. This makes building robot swarms way simpler, cheaper, and probably a lot more robust. And that kind of leaves us with one final big question. We just saw how a single, almost invisible law of physics can create all this order and motion and complexity that looks, for all the world, like it's alive. It just makes you wonder, what other simple, elegant rules like this are out there, quietly orchestrating the universe all around us, just waiting for us to notice?